Lagrange multipliers give us another way of looking at constrained optimization. So we're with the same basic setup. So we want to maximize some objective function subject to some constraint, and the constraint is given by a constraint function being fixed equal to something. And Lagrange's idea, his kind of insight was he said, oh, you know what, that constraint equation, we can think of that as being actually the level curve of some function that's providing the constraint. And then we can look for a relationship between this function and that function. And it's a bit subtle, but I think this picture gives a good idea for how it works. So take a look at, I've got on the left here a plot of some random function I cooked up. And then on the right, the contours or level curves of that exact same function. And so you can see that there's some, if we want to find the maximum and minimum value of f inside this circle, or inside this disk rather, then let's see. So there's some local maxima at these points right here. But this one seems to be the biggest. It's the most red, so it's definitely the highest one, right? So the possibilities for where the function obtains its maximum on this disk are that it can happen at a local maximum inside, or it can happen on the boundary. Same thing for minimum values of the function. So we can look at the local minima, like here's a local minimum, here's a local minimum, here's a local minimum. The minimum value is going to happen at a local min inside or else on the boundary. And by the looks of it here, it looks like probably somewhere down around here is going to be the lowest point that occurs on this disk. So now take a look at the geometric relationship between this constraint curve, this curve coming from this level curve coming from the constraint equation, and the level curves of the function itself. And so let's take a look at the maximum value of this function. I think we probably agree that the maximum value occurs somewhere right around here. So let's take a look up close. What we see is that if we are on, say, if we're at this point right here, notice that you could improve, actually here, let me back it up and let's put it over here so that on the curve itself, that's probably, or on the surface itself, we're probably somewhere over here. So this point, where would you go to make the value of the function bigger? Well, you can see that you'd want to go up, right? And you also can see that if you go over to the other side, there's going to be somewhere on the back side of this hill, there's going to be that other point there where it's at the same height. Yeah. Now, if we go up a little bit to closer to the peak, then we're on some other level curve, and there's going to be some other point around the other side where we're also on that level curve. And the only place where that stops, so let's see, so maybe I can try and draw the level curves. Okay, this is going to be kind of dicey, but I guess we got, here's the level curve for all the points at the same height on as the red one. And then here's the ones that are all the, oops, I guess I drew that all sort of terribly. Hold on, whoop! Dang it, I destroyed it. Okay, sorry. Okay, there's the red one, and then the purple one would be something like that. Okay, and you can see that if I got it just right somehow, like maybe in between, in the middle of these, there would be some curve right through here that it would just be tangent to. So it just kisses it tangentially. That's going to be the last level curve that this constraint circle or disk touches before it sort of gets out of reach. And since it's the last one, that means it's the one where the function takes the highest value. So that point is exactly what we're looking for. And similarly, if we are looking for minima, you can see that the function value here is bigger than the function value here, is bigger than the function value here, here. The very smallest that it gets is going to be on the one that's tangential to it, down there in the very bottom of the pit. And that corresponds to, oh gosh, drawing these level curves over on the other one is going to be a nightmare, but maybe around here, and then around here, and then around here, and then somewhere it goes just outside. And the very last one where it touches tangentially, that'll be the one that we're looking for. So the thing is, asking where two things are tangential to each other, that's a hard question. But it's very closely related to an easy question. And the easy question is, where are two things parallel? So now, let's go over here and take a look at what the largest value of f is sort of in this neck of the woods. I'm just doing this so that we have a bit of a clearer picture because I've already drawn a bunch of junk over on that other one. The gradient is always orthogonal to the level curves. So the gradient is going to be looking something like this as we go around. Now, if I look at the gradient of the constraint function g, then it's going to be, say the function g here is x squared plus y squared equals, we're centered at the point half, one half, one half, one half, so that's not going to do any good. I would need x minus a half squared plus y minus 1/2 squared. And then we've got a radius of, I don't know, maybe like something like this. Okay, so then the function g that we're looking at as our constraint function right here is this guy. And this green circle is the circle where g is equal to 0.2. All right, the function g is growing as the radius of the circle grows, right? From that, we know that the gradient is going to be, for the green guy, is going to be pointing outward always. Straight out. So all these little lines are supposed to be pointing from the center directly outward. And then if you notice, as we connect the dots right here through the middle, the point that we're interested in, the highest, or the point where we are have the highest value of the function, that corresponds to the location where the two gradient vectors are parallel. So let's do that again over by where we were looking for the minimum here. So this, we're looking at where this, here's the gradient vectors of my, coming from G, my constraint. And then if I look at this tangent level curve down here at the bottom, its gradient is going to be pointing like this, and like, oh wait, I just realized I'm going backwards. This is at the bottom here, so we would actually, the gradient would be pointing, go up the hill, up the hill, up the hill, up the hill, this way. And right here at the point of tangency, we've got a red arrow going one way, and we've got the green arrow going the other way. In other words, it's going in exactly the opposite direction, which means that they are parallel. So remember, for vectors, saying that u is parallel to v, this means that u is a scalar multiple of v. So since the particular vector field that we're looking at right here is we've got the gradient of g giving us all these little green arrows, and the gradient of f giving us all these little red arrows. What we want is we want to have the gradient of f be parallel to the gradient of g. And that's our method. That's Laplace's insight. So Laplace multipliers. We're going to solve gradient of f equals lambda gradient g, and g is equal to c. So that's going to be our system. Now, what is lambda? We don't care. We just want to know if there is a lambda that does it. Now we'll be able to solve for the lambda while we find the solution to this system, but it doesn't mean anything that we really care about a whole lot. It's just, if we can solve the system by finding a lambda, then it shows that a lambda exists. And if such a lambda exists, then that means that we've got exactly this parallel condition that's telling us things match up, and we're finding sort of the last level curve inside the constraint set, which is exactly what we want. And I guess the last thing to say before we do an actual example is maybe a bit of motivation. Like, why would you actually want to do this like crazy stuff with matching the gradients up like this? Well, the other technique that we saw before required you to solve the constraint in terms of one of the variables, and sometimes you can't do that, or it's really hard, or it makes things that are so complicated that when you substitute them in and look for the constrained critical points, the equations that you get are just so nasty. So the trade-off is, instead of a couple of really horrible equations, we instead have now more equations, because this system here is going to give us an equation for every variable in f, and then also the constraint. So we'll get more equations, but typically they'll be much simpler and much easier to solve.